the videos were misplaced, the numbering, and yesterday I put them in order, yesterday night, in sequential order. So if you had troubles now, if you had a trouble to see them, now they are fine. Okay, so basically, I just would like to remind you, here there are some links, and there are also a couple of links to a couple of floods. And here there is a click to a short clip of a flash flood that occurred here close to Bologna. And I think there is another clip linked here of another flood that occurred last year in Piacenza, in this region. I'm providing these links to give you an opportunity to see some videos of floods, because as I told you, I think it is extremely important that you observe and you try to understand what is behind the mathematics that we try to build. And there are several videos on YouTube of floods, a lot of them. And I suggest you to have a look. Of course, not all of them, because it takes weeks to see all the videos, but just spend some time observing. And needless to say, if you have a chance to see with your eyes a flood, I think this is an opportunity that should be taken by taking care, because it's extremely dangerous to get close to a river during a flood, but extremely. Let's say that it's dangerous if you don't take care. If you take care, of course, it's not dangerous. And I suggest you, when you get the opportunity to look at the floods, to go there and get an idea. Okay, so basically we got to the stage where I clarified to you some basic concepts of probability theory, and I explained the concept of probability distribution. Okay, and here there are some links. I want to update the lectures, these notes, by including the explanation that I provided to you last Friday before starting with the exercise, the explanation that made the difference, explained what's the difference between the probability or probability Px, capital Px, where x is the considered random variable, and probability is also called cumulative probability, and the probability density. The probability density, lowercase p, of the same random variable x. I explained what is the difference, and basically what I said is that the probability is the integral of the probability density for continuous variables, of course, over a specified domain. So basically, I may say that capital Px is the integral between two values, x1 and x2, of lowercase p of x in the x. And basically, what is this integral? Is the probability of getting an outcome from the random variable x falling between x1 and x2. Okay, so this is what I explained. And I hope the concept is clear. I now assume, from now on, that the concept is clear. The difference between probability and probability density is clear. And remember that these apply to continuous variables. Continuous variables. Okay? If it is not clear, just let me know. Okay? Because I don't want to be too much detailed, because my perception is that you are quite well prepared. So I don't want to, to dedicate too much time in explaining things that you already know. Okay? So, but if my perception is not appropriate, just let me know. If you still have some things that are not clear, some concepts, just let me know, and Also, we may arrange an appointment besides the lectures to clarify that. Okay, so this is the stage where we got, and let me just point out that the probability, I told you, is also called cumulative probability, and in some cases it's called probability of not exceedance. And when you integrate between x1 and x2, x1 could be the lower extreme of the interval of definition of x. So let's suppose that x is defined between minus infinity and plus infinity. Like, it's difficult to make an example in hydrology, because in hydrology usually variables have a lower interval that is 0. But let's suppose that we have a random variable that is defined between minus infinity and plus infinity, okay? And in this case, if you take this integral, and allow me to rewrite because the blackboard is very small, and you take the integral from minus infinity to x2, this is called probability of not exceedance of x2. And in this case, we may write it in this way, capital P of x2. And again, I would like to stress that it's the probability of not exceedance. What is the reason why I want to stress this concept? Because in hydrology and hydraulic engineering, we often talk about probability of not exceedance of a river flow value. And in this case, the integral, it's computed between 0, because the river flow is defined between 0 and plus infinity. So, when we talk about probability of not exceedance of a river flow, we usually, allow me to write here, denote it as capital P of Q, and usually this is the integral between 0 and Q of P, let me say Q star, P, Q, lowercase p in the Q. The lowercase p I indicate it with this symbol, okay, in order to make the difference between the capital P and lowercase. So basically, if you compute the integral of the probability density between 0 and Q star, you get something that is called probability of not exceedance. And this is something that I want to clarify, because it's also sometimes found in the textbooks, this concept. I hope this is clear. Okay, so what did we learn so far? We learned that it would be extremely useful to have an analytical function describing the probability. Probability or probability density, it doesn't matter, because you can derive the probability density by taking the derivative of the probability. And you can derive the probability by integrating the probability density. So it would be extremely useful to have an analytical function describing, for a given random variable, for a given process like floods, describing the probability. So ideally, it would be really nice to have a function, an analytical function, PQ, where P can be probability of not exceedance, for instance. It would be extremely useful, because this allows us to get an estimate of what? Of the peak flow that we may expect from a given probability. And the probability I will show you that can be related to the return period, which is something that is intuitive. We already studied the concept of return period, average time between two events, which have a magnitude that is equal or higher with respect to a given value. And a return period means frequency is related to frequency, and frequency, we know, it's related to probability. So basically, if we had this analytical function, I already mentioned this concept to you, that gives the probability for a given river flow, then by relating the return period to the probability, we can estimate the river flow corresponding to a given return period, which is our problem. It's the design flow estimation. So this suggests a first method for estimating the peak flow, which is actually a probabilistic method. But we can give a physical interpretation to this method. I will tell you later what the physical interpretation could be. Okay, so does it exist a function? Does the literature, the theory, provide functions, analytical functions describing probability? The answer is yes. And you know that it's yes, because you already studied in your background, I assume, something related to probability distributions. There is a probability distribution that is very famous, let me say, which is the Gaussian distribution, which is introduced in these notes. And the Gaussian distribution has, you don't have to learn it by memory. It has an expression for the probability density, which I took from Wikipedia, so the symbols are a bit different. It is indicated with lowercase f instead of lowercase p. So please bear with me, be patient about this difference, but the concept is anyway clear. And basically this is the probability density function of the Gaussian distribution, and you don't have to learn it by memory. The only interesting thing to see here is, not the only, one of the interesting things to see here is that there is indeed an analytical function describing the probability density of a given outcome, lowercase x, from the random variable x, depending on two parameters. And two parameters which compare in the analytical expressions. What are parameters in a function? Parameters are usually constants to be estimated. So these are constant quantities in analytical functions that are to be estimated. Once that you estimated them, they are constant. And what is the purpose of parameters? The purpose of parameters is to make an analytical function flexible. So basically, what is the purpose of introducing parameters in a probability distribution? To make the probability distribution flexible, to adapt to different phenomena. Okay, so the parameters, again, are constants to be estimated. Once that you estimated them, they are constant. This means that the probability distribution can describe a lot of processes. But once you have estimated the process you are interested in, you estimate the parameters of the distribution, and then the distribution becomes fit to the purpose, and the parameters remain constant. It is clear? Is it clear? And there are two parameters here. Probability distribution may have one parameter, two parameters, 3, 4, 5. There is no limit. The more the parameters, the more the flexibility. But the more the parameters, the more problematic it is to estimate them. Because this is a problem for the engineer, of course. You select the phenomena you are interested in, the phenomenon, like flood of the Po River at Ponte Lagoscuro, and then you have to estimate the parameter, and this is a task for you. Because you need to define this analytical function to be able to derive your design flow, and then you need to estimate the parameters. And of course, we have to learn how to estimate them, but it is intuition, it is intuitive, that the more the parameters, the more complicated the task is, okay? So, basically this is, as I said, the shape, the general shape for, different, not fixed values so far of the parameters, mi and sigma. We will see what they mean. But so far, you may assign whatever value you want these parameters, And you may also want to draw in a graph, in a picture, the shape of this analytical relationship. And the shape is depicted here for different parameter values. And this is from Wikipedia. So basically you see that for different values of mi and sigma, you get different shapes. First of all, please note that this distribution is defined from minus infinity to plus infinity. And you can see from this picture that it's symmetric. I'm talking about the Gaussian distribution, which is also called normal distribution. It's symmetric, and it's defined from minus infinity to plus infinity. So first consideration, I just told you that in hydrology we have positive variables in general, not always, but in general we have positive variables. Rainfall is positive, river flow is positive, which means that the Gaussian distribution is not really the best distribution to describe these variables, because it is defined also on the negative numbers. So this is a first connotation, a first consideration. Second, let me just make some reflection on the shape. It's symmetric, which means that there is a value of the random variable x which divides the probability distribution in two parts. One which is on the left of this value, the other one is on the right. And the distribution gives symmetric probabilities on the left part and right part. So what is this value that splits the probability distribution, the Gaussian probability distribution, in two parts? What is this value? It can be proved that it is the average value of the random variable x. It's the average. And therefore, what we can say is that the Gaussian distribution is symmetric around the mean, or the average. Average, mean, they are synonyms. Not really, but let's say that we are using here them as synonyms. So again, I repeat, the Gaussian distribution is symmetric around the average. And if I look at the left part, probability, it gives the same probabilities with respect to the right part. So my question for you would be, is it reasonable for flood flows? Is it reasonable that we take a symmetric distribution around the mean to describe flood flows? Okay, let me give you an example. If you take whatever river, a river that is close where you live, and you take the numbers, the data, and for instance, you take the daily river flow data. You may have daily river flow, monthly river flow, or hourly river flow, where daily, monthly, hourly is the time step at which river flows are observed when collecting the data. So let's suppose that you have data, and let's suppose that you have daily river flows. Okay? If you compute the average is close to zero. You would realize that it's close to zero. Or let's say, to provide you an example, for the Secchia River, which is a river that is a tributary of the Po River, which flows close to here, if you compute the average of the daily river flows, it's about 16, 18 cubic meters per second. So it's very close to zero. If you look at the maximum observed river flow in the past 50 years, you get close to 800 cubic meters per second. So you see that the average is much closer to zero than the distance from the average to the maximum value. So you understand that it's not symmetric. Okay? The average is not placed in the middle of the interval of definition. It's much closer to zero. Okay, this is something that you can easily see by making an experiment. And it's something that I may stimulate you to try. You can find on the web several time series of river flows. I may provide a link here, but there are many of them. If you look on the website of the United States Geological Survey, there are time series, long time series of daily, hourly, monthly river flows for many North American rivers. And you can make this simple experiment, compute the average, and see the distance between 0 and average, and the distance between the average and the maximum. We may make an experiment right now, later on maybe. So, what is the conclusion? The conclusion is that, you know, this distribution is not a good description. In fact, if we look at the probability distribution of river flows, they usually appear in this way. EXX, so basically you see something like that. With a long tail. So we typically say that the river flow is characterized by a long-tailed probability distribution, a long right tail. Okay. But this is an interesting example, the Gaussian or normal distribution. And why it's interesting? For many reasons. And the first reason is mathematical tractability. There is the problem that it cannot be integrated analytically. This relationship here, if you try to compute the integral analytically, you don't succeed. You have to compute it numerically. So this is a bit of a problem. But apart from this problem, aside from it, it's very tractable. And there is also another interesting thing, which is much interesting, and I would like to mention this fact to you, because it's, I think it is, you know, for engineers, it's not really something that it's interesting from a practical point of view, but it is very interesting from, from the point of view of a student. And let me clarify what is this interesting feature I'm talking about. For the Gaussian distribution, I write it here, Gaussian, the central limit theorem applies. And don't be concerned, I'm not now starting a proof of a theorem. I'm just providing the information. What does it mean, the central limit theorem? It means that whatever random variable you are considering, continuous, of course, rainfall, river flow, or growth of potatoes, number of potatoes growing in a field, and whatever is the random variable, let's suppose that it's a random variable that depends on time, like river flow. River flow is observed at a given time, rainfall is observed at a given time, growth of potatoes is observed at a given time. So let's suppose that it's a time-dependent variable. And let's suppose that you average this variable over intervals of increasing length, like river flow. Let's suppose that you have hourly river flows available, and let's suppose that you average to get daily. And then let's suppose that you average again to get monthly. And let's suppose that you average again to get annual. The central limit theorem says that whatever random variable, depending on time, continuous, you are considering, for increasing length of period over which you are averaging, so for increasing averaging period, the random variable converges to the Gaussian distribution. So whatever random variable you are considering continuous and dependent on time, by averaging over increasing length periods, you converge to the Gaussian distribution. This is extremely interesting because it means that in the chance, in randomness, there is a rule. Because as I said, this happens for whatever events. It means that if you are looking at river flows and you average and average and average, you get to this distribution. This is much interesting. From a technical point of view, we don't use it. But what is interesting is that you know, because I just told you, that river flows are characterized by this probability distribution that is long-tailed. But this applies for river flows observed over short periods. The periods that are technically interesting from a technical point of view usually are hourly, daily, so the probability distribution is indeed asymmetric and long-tailed. But if we average it, the river flows over the monthly time scale, the annual time scale, we get closer and closer to the Gaussian distribution. This is why the Gaussian distribution is so important. Okay? So these probability distributions that are not symmetric, they are called also asymmetric. They are also called skewed. I'm not explaining to you why. I don't want to spend too much time on probability theory. It's just a part of this subject. So I'm not explaining why they are called skewed. Skewed is basically a synonym of asymmetric. There is another important thing that I wanted to tell you. In general, when I talk about a random variable, I use the symbol X when it is a generic random variable. When it is a river flow, I use usually Q. But an important consideration on notation, because it is applied by many textbooks. It is convention, usual convention, when we use a symbol to denote a random variable, to use the capital when we talk about the random variable. So if I talk about river flow, not a specific value, but the process, river flow, I say the river flow, I call it Q, capital Q. When I talk about a specific value of the river flow, I use the lowercase. This is a conventional notation that is used by many textbooks and allow you to see the difference between a given value and the process. And the given value is called an outcome. So you define a random variable x, which represents the random variable as a broad, the collection of all the possible values, and lowercase x is called an outcome, which is a precise value from the random variable capital X. This is just a consideration on notation. Sometimes, for the sake of brevity, I don't make this difference. But when you go to a textbook, you will find this difference. And you may get lost a little bit. Like in this case, you see that it's lowercase x because this gives the probability density of this outcome, lowercase x. It is not really very important that we understand this difference from a technical point of view, but if you then go to study on different sources, then you may get lost if you don't understand this difference. Notations are boring, but on the other hand, they are useful. Because once that you know them, it's easier for you to understand what is written in a web page, in a textbook. And there is to say that sometimes web pages and also textbooks, sometimes they don't respect the notation. So it's much better to be able to see when something is written in a formally correct way. And in order to do that, you must know notation, unfortunately. Okay, so this is an example of the Gaussian distribution. But on the other hand, let me go back to our original problem. We have to estimate a design flow. And I said, great, if I had a probability distribution, PQ, my problem would be solved, but we still don't know how in practice. And we know that this probability distribution cannot be the Gaussian, because when I'm talking about floods, usually in the technical domain they are observed at fine time step. I need to define them at fine time step, and therefore I need a skewed distribution. So basically the Gaussian distribution is not useful to the purpose. Okay, so let's see what is a distribution that we may use. And let's go into the explanation of a very classical method for estimating the peak flow, very classical, which is the annual maxima. And I think you already know it. And can I make a poll just to understand what is the target? How many of you raise your hand if you know the annual maxima method? Nobody. Perfect. No, it's much better. It would be a difficult situation if half of the hands were raised. Okay, perfect. This is, as I said, a very classical method, and I adopted what I consider a new approach to this subject, but on the other hand, I told you, this new approach, of course, must also include the treatment of the classical methods. We must know the new methods, the innovative methods that were recently proposed, but on the other hand, we must know the classical methods. And this method is based on the application of a probability distribution. And it's often called a probabilistic model, or probabilistic approach, or data-based. I already told you that I consider that we can provide this method also physical interpretation. And this is new. But the method in itself is very classical. You can find it described in many web pages and many textbooks. I think there is also a Wikipedia page. If there is, it is linked here. But anyway, this is not important for us. Let me define this method. So basically, what is the purpose? The purpose is to fit the probability distribution of the peak flow values. And this method is very classical, so it dates back, it was proposed about 100 years ago. They started using it in the 1930s, 40s. And at that time, they didn't have much computing power. So basically, even if they had many observations available of river flows, they wanted to limit the number of observations that they were analyzing. They want to limit, because now we can deal easily with millions of numbers, millions of observations with the PC, but they had to write their analytical computation on a paper, and therefore they want to limit the number of observations. So the rationale was, why should I analyze the frequency of occurrence, the probability of all the data? I am interested in floods, so let's limit our attention to the floods. This was the idea. To forget about low river flows, to forget about values that one may see every day, but to concentrate on the highest values. Because they assumed that the probability of occurrence, the frequency of low flows, was completely different by the frequency of high flows, which is true indeed. But on the other hand, today, research proved that when approaching these problems, there is uncertainty. And uncertainty can be reduced by increasing the information. And therefore today the tendency is to try to make use of all the information available. Today, you know, rejecting observations, discarding observations is something that should be carefully considered, because they are observations from the same process. We are talking about river flows. In the past they separated, they said drought or low flows are originated by a different process than floods. And therefore they divided the domains. But on the other hand, if we look at the physical basis, the processes are the same. The physical laws are the same. So by considering the whole information, we get a better perception of the process. So today, this is something that, you know, it is still applied for the sake of rapidity, simplicity. And also it's still applied because, you know, there is research results, before getting into the professional domain, they take some time. But at that time, it was nevertheless a very good idea, because they didn't have any possibility to deal with like 15,000 of numbers. Today, for instance, if I look at the Po River, the time series of the observations, it's 90 years long, and they are daily observations. So if you multiply 365 times 90, you get something like 32,000 of numbers. 100 years ago, they didn't have any possibility to handle this huge amount of information. Today, we can. Okay, so what was the idea? The idea was to focus on the flood flows, and the idea was to get for each year the peak flow. So from each year of observation, let's suppose that they had this hydrograph